Look at the physical hardware powering modern AI. A single GPU physically cannot hold the memory required to train today's massive language models. A high-end GPU maxes out at 80 gigabytes of VRAM, but a massive model requires 140 gigabytes just for its weights. Adding gradients increases the memory burden, and optimizer states push the total training requirement past 500 gigabytes. You cannot compress 500 gigabytes of active training data into an 80 gigabyte ceiling. Attempting to run this on a single NVIDIA H100 GPU results in an immediate out-of-memory error. The mathematics of foundation models exceed the physical limits of individual hardware nodes. This mandates a new approach to compute architecture. The intuitive fix is to simply network more GPUs together. For years, the standard method for scaling across multiple nodes was Distributed Data Parallelism, or DDP. DDP partitions the incoming training data, but forces an identical 500 gigabyte replica of the entire model onto every single GPU in the cluster. Because it offers zero memory savings per device, every node immediately runs out of memory simultaneously. Scaling compute power is ineffective if the architecture relies on memory redundancy. Since replication fails, the only path forward is to fracture the model itself across the cluster. This is the logic behind Microsoft's DeepSpeed Zero Redundancy Optimizer, Zero, and PyTorch's Fully Sharded Data Parallelism. Zero Stage 1 targets optimizer states, distributing them across 4 GPUs. Stage 2 shards the gradients. Finally, Zero Stage 3, FSDP, fragments the parameters. Each GPU now holds exactly 1/4 of the footprint, fitting safely within the 80 gigabyte limit. By sharding the model's geometry, Zero and FSDP prevent out-of-memory errors at scale. This creates a new operational challenge. Because each GPU only holds a fragment, the nodes can no longer independently calculate a forward CAS. To solve this, we use an all-gather operation. GPUs must fetch their missing parameter shards from other nodes across the network just in time for calculation. During the backward pass, a reduce scatter operation synchronizes the calculated gradients back to their home nodes. This architecture involves a significant performance penalty. While FSDP reduces memory usage by over 60%, training time can increase by up to 6 times due to network communication. Solving the memory wall immediately hits a communication wall, where compute throughput is limited by how fast data can move between nodes. When models grow so large that sharded data parallelism alone saturates the network, we must implement model parallelism. Tensor parallelism slices one layer's matrix math across 8 GPUs simultaneously. Requiring constant communication, it stays inside one server. To scale further, pipeline parallelism slices the model by depth, assigning layers 1 through 10 to server A and 11 through 20 to server B. This introduces the pipeline bubble, where server B sits idle while it waits for server A to finish its portion of the batch. Orchestrating 3D parallelism requires mapping software algorithms onto the physical geography of the data center. While FSDP overcomes the memory wall, it generates a massive volume of network traffic. Without the correct hardware to support these communication spikes, training stalls. Inside the node, NVLink 4.0 provides 900 gigabytes per second of bandwidth. This is the physical engine that makes tensor parallelism possible. Internode communication relies on a non-blocking fat tree design using Quantum 2 InfiniBand, providing 400 gigabit per second connections between servers. This hardware specifically prevents the collective communications required by FSDP from bottlenecking the main training loop. Software sharding is only effective when supported by an ultra-low latency hardware backbone. On the macro scale of an integrated AI supercomputer, these components operate as a single system. Massive datasets stream via tar shards directly from blob storage into the cluster memory, bypassing traditional I/O bottlenecks. The orchestration layer, managed by Zero3, dynamically coordinates what data shard lives on what node across the fabric. This configuration enables the training of language models exceeding 1 trillion parameters. At this scale, the traditional standalone server is effectively obsolete. Modern AI training treats an entire data center rack as a single, tightly coupled computational brain. The memory requirements of foundation models fundamentally exceed the capacity of isolated GPUs. These physical limits necessitate 0 and FSDP sharding, which in turn require 3D pipeline distribution and high-speed InfiniBand hardware to function. When out-of-memory errors strike, throwing more GPUs at the problem is a waste of capital. Re-architecting the distributed parallelism strategy is the only effective solution. You can find the DeepSpeed whitepapers and the Azure AI architecture documentation in the links below. In the era of massive AI, system architecture dictates the fundamental